Today, I'm going to explain how airplanes weigh thousands of pounds, yet fly effortlessly through the sky. The secret is in the wings and something called lift. There are four main forces acting on any aircraft at all times: thrust, drag, weight, and lift. Thrust moves the plane forward. Drag resists that motion. Weight pulls the plane toward Earth's surface. And lift? Lift is what pushes it upward into the sky. For an airplane to take off, the lift force must exceed the weight. For it to accelerate forward, the thrust must be greater than the drag. But once it reaches cruising altitude, the lift equals weight to maintain a stable flight. Let's zoom in on the wings of an aircraft. Viewed from the side, an airplane wing looks like this: curved on top, flatter underneath. This shape is called an airfoil and is the cross-section of the wing. The way air moves around this shape is key to understanding lift. Here is some important vocabulary to help us out. The leading edge is the forward part of the wing, seen from the front of the aircraft. The trailing edge is the back of the wing, seen from the rear of the aircraft. The trailing edges of an airplane wing are usually very thin compared to the leading edge, and I'll explain why later. The chord line is a straight line connecting those 2 points. We'll be using this chord line to talk about the angle of attack more in a later video. The camber is the amount of curve on top of the wing. Alright, now on to lift. Lift is generated in many ways. What we are tackling today is a difference in pressure above and below the wings. The bottom of the wing is a higher pressure region than the top of the wing. The difference in these pressures generates a lift vector. Let's break this down. First, I'm going to show you why the airflow over the top of the wing is actually faster than that underneath, and it has everything to do with the shape of the airfoil. When a plane is flying, it's slicing through the air at a high speed. As the leading edge of the wing comes in contact with this incoming air, it splits the flow. Some air goes over the top, some goes underneath. The air on top has to travel around a longer, curved path. So one might assume that in a race to the trailing edge, the airflow underneath would win. This is actually not the case. The air above is not even trying to meet at the same time, which is a common myth supported by the unsupported equal transit theory. In reality, the air over the top reaches the back of the wing even faster than the air underneath. That means it must be moving more quickly. Let's find out why. As the thick front of the wing meets incoming air, it compresses it, creating a high-pressure region. But farther back, on the top of the wing, the surface curves away from the flow, shielding that area from the air, creating a kind of vacuum or low-pressure shadow. The difference in pressure between these two regions drives the airflow as it rushes to fill that shadow. The air accelerates as it's pulled across the curved top. So the airflow is significantly faster over the top than past the bottom. In fact, air particles that travel on top will reach the back of the wing before the air underneath, even though the actual distance they have to travel would suggest otherwise. Bernoulli's principle supports this, telling us that in a fast-moving fluid, like air, pressure and velocity are inversely related. Since the speed of the airflow above the wing is greater than below, we know that the pressure above the wing is less than the pressure underneath. This difference in pressure from top to bottom results in a greater upward force, creating a lift vector that helps the plane stay aloft. The shape of the airfoil is critical for generating maximum lift. The camber, or the amount of curve on top of the wing, can alter the amount of lift. The more the top of the wing curves, the greater the difference in pressure between the two regions are, resulting in a greater acceleration as the air shoots to the back of the wing. And remember Bernoulli's principle, faster air means lower pressure. So a cambered wing exaggerates that pressure difference between the top and bottom, meaning more lift. One cool thing about cambered wings is that they can generate lift even when they're flying level, at zero angle of attack, because the shape alone creates a pressure difference. But camber comes with a trade-off. More camber means more lift at lower speeds, which is great for gliders or birds, but it also increases drag, which slows the plane down. That's why faster planes, like jets, usually have less camber and rely more on speed and angle of attack to get their lift, which we'll go over in a future video. Of course, this is just one way to understand lift. In the next video, we'll explore how lift is also generated through Newton's third law, by pushing air down to go up.